Hello, this is Gaurav Kopodi, pursuing bachelor's at Indian Institute of Roorkee. I am going to give a presentation on Hall effect experiment. These are the apparatus which are going to be used to observe Hall effect. First is Hall effect setup, which basically connected to Hall probes. Its job is to supply current to Hall probe and measure the Hall voltage developed. Second apparatus is Hall probe. It contains semiconductor material such as gallium arsenide, which is required to observe Hall effect. Another apparatus is an electromagnet, which is basically used to generate magnetic field. Two more apparatus which is needed are Gauss meter and a constant current power supply. Gauss meter used to measure magnetic field generated in electromagnet with the help of Gauss probe, and constant current power supply is required to supply current to electromagnet. Magnetic field in electromagnet can be varied by varying current in current power supply. So the basic theory behind Hall effect is when a semiconductor or conductor carrying current is placed in perpendicular magnetic field, perpendicular to direction of current I mean, charge carrier experiences a Lorentz force, which is perpendicular to both magnetic field and the direction of current. This causes the building of charges at the top and bottom end of sample and potential difference develops. We call this Hall voltage. Charge continues to build up until both electric force and Lorentz force balance out each other. If we measure the Hall voltage, which we can determine the Hall coefficient given by this expression, which is shown in the slide, which can be used to calculate charge carrier density in a semiconductor. We can also obtain the information what type of carrier present in semiconductor if we know whether the Hall voltage is positive or negative. So here is the demonstration of first part of experiment. Here to measure the magnetic field generated by an electromagnet, I am placing a Gauss probe inside of electromagnet. Measurement is visible on Gauss meter panel which tells us the magnetic field strength. And then I am placing an Hall probe in electromagnet knowing the knowledge of magnetic field strength. Hall probes are connected to Hall effect setup which tells us the Hall voltage value for the corresponding magnetic field. We repeat this multiple times for different magnetic field value and record the Hall voltage, keeping the current through Hall probe at constant value. This is the observation we got for the first part of our experiment. We can see from this by increasing the magnetic field, magnetic magnitude of Hall voltage increases and Hall effect becomes more evident. In the case where the direction of current is reversed, can be simply done by placing the Hall probe upside down relative to the forward case and Hall voltage comes out to be negative. Because charge accumulation takes place in opposite manner as the force experienced by charge carrier is opposite. So this is the second part of our experiment. Here I am setting the magnetic field at a particular value, and after that I am going to place Hall probe inside an electromagnet knowing what the magnetic field is. We change the current through Hall probe through Hall effect setup and record the corresponding value of Hall voltage. This is the observation we got for second part of our experiment. The observation is for a p-type germanium crystal. Hall voltage, we can see that Hall voltage varies linearly with the current. The slope of this linear variation can be used to calculate the Hall coefficient. In this image, it is shown if we know the slope, we can calculate the Hall coefficient, which further tells us about the charge carrier density in a semiconductor and mobility of those carriers given the resistivity of semiconductor is known. You can also see that Hall coefficient comes out to be positive, which tells us that this is the semiconductor is positive. So with this, I conclude my presentation. Thank you.